Honors Algebra 2, Chapter 3. We're going to throw in a little Section 1, but mostly Section 2. The chapter is split into two parts. The first part is all about solving systems of equations. The second part is using matrices to solve systems. So the first part, algebraically, we're going to look at, and there's a lot to get through today. Hopefully we can squeeze it in. So systems of equations is just a set of equations joined by the word and. So the word and is noted by this symbol, this brace. This brace is saying that these two equations are describing one situation. So a solution to a system is an ordered pair that satisfies all conditions. So all the conditions or equations have to be true for a point to be a solution. So this example is 2, 5, a solution to the system. You would actually need to plug 2 and 5 into this equation and check it. If we do that, that checks, we get 9 equals 9. But you also need to do the bottom. If we do the bottom, we get what? 8, 13 equals 3, which is not true, so this point is not a solution. And so you have to check all the conditions to make sure a point is a solution to the system. Looking for solutions graphically, and this is really what 3.1 is looking at, is graphically. To solve graphically, you just graph all the conditions. So you want to graph all the conditions, all the equations, using our knowledge from Chapter 2, and then you're going to find the point of intersection. The point of intersection is the xy value that makes all the equations true. So for this example here, this point where the two lines intersect has an x value right here and a y value that makes both these equations true because it's on the line for both equations. If there's no intersection, then there is no solution, and that would occur for parallel lines, and so we'll talk about that later on. Since the solution is a point xy, where x and y are the same for both equations, we can substitute equivalent value for a variable. So this is the first method, substitution, first algebraic method, substitution. So in this one, we know that y equals this quantity. So y is the same as this quantity, 2x plus 1. So in the other equation where I see y, instead of writing y, I can write what I know it's also equal to. The y is equal to 2x plus 1. So what we're doing is we're substituting 2x plus 1 in for the y. So we'll state that again. We're substituting 2x plus 1 in for the y in the other equation. When you do that, we no longer have a y, we only have x's. And that's the key. When you're solving systems of equations, you need to go from two equations, 1, 2, down to only one equation. So now we have one equation, one variable. And we can now solve this using our basic algebra. So we add 3x to both sides, subtract 1, so we find that x is 1. After you find that first 1, you're not done. This is just part of your answer. We know that the x value is 1. We need to back substitute. So we back substitute, which means take the answer we just have, the answer we just found, and plug it back into one of these equations up here to find y. It doesn't matter. I'll just choose the first equation, and we plug in 1. So then y is going to be 2 plus 1, or 3. So our final answer is going to be the point 1, 3, the x and y value. And you can plug it back into both equations to make sure it checks. Another example here. So this one, they're not both y equals. One is in standard form, one's in slope-intercept. That's still a good setup for substitution because this one here, we know this is equivalent to y. We know 4x plus 1 is y. So in the other equation, we can put it in for the y. So 3x plus 2y, but again, instead of writing y, we're going to write what it's equal to, 4x plus 1. That's the substitution, equals 10. Then we have to use our solving technique again. So 3x plus 8x plus 2 equals 10. Combine the terms, so 11x equals, I'm going to subtract the 2 as well. So we have 8. So x is 8/11. Not very pretty, but that's it. That's the value for x. So we're going to back substitute that. I'm going to choose the second equation. So y equals 4x plus 1. When you plug in the x value, 4 plus 1, So this is 32 elevenths plus 11 elevenths. Just using mental math. Let's do 43rd elevenths, which we could write as 3 and then 10 elevenths. So it's the y value. So there's our x, there's our y. Sometimes to use substitution, a variable needs to be solved first. So like in this example, we don't have a variable x or y solved. We don't have it isolated, so we can't use substitution. So we first need to isolate one variable. And it doesn't matter which one you isolate. I'll actually choose to isolate this x right here. I think it's the easiest one to isolate because all I have to do is add y to both sides. If I isolate that, that's equivalent to x equals y plus 1. So you add y to both sides. So now in the other equation, we can take what x is equal to, x is y plus 1, and put it in place of x right here. So in the second equation, it's 2 times the quantity, y plus 1, and then we still have minus 3y equals negative 1. So now we got rid of the x's. So we have one equation, one variable. It's okay, it's the y. So now we can distribute, combine like terms. So we have negative 1y. Subtract 2. And so we find y is 3. And so now we have y, so you back substitute into any equation that has x and y. And I would actually choose the equation we have solved for x. Typically it's less work, less solving, so you just have 3 plus 1 as the answer. So x is 4. So the 0.34. Another method, linear combination, is what is sometimes called in textbooks. All you're really doing is adding or subtracting the equations. And so you take these two equations, and this is a great method if you get them both in standard form, where like you see how the x is above the x, the y is above the y, the constant is above the constant, the equals are lined up. So it's all kind of in the same form. Then it's pretty easy to set up. If we just add these two equations, and we add straight down the column, so x plus x is 2x. We do a y plus a negative y, we actually get 0y, and that's what you want to occur here. And if you do the same thing with the constants, 63 plus 12, so you get 75. And so we don't have any y, so all you have to do is divide both sides with 2 to find the x. So you find that x is the 37.5. Now we still have to back substitute that. A little easier though with these equations. It doesn't matter which one. I just take we'll take the bottom one here. 37.5 minus y equals 12. So if you subtract 37.5 to both sides, you get negative 25.5. And you divide by the negative, so you find it's 25. 25.5 is the y value. So you have y, you have x. Similar setup here, and so they're positive. So we add here, it's 4m plus 4m is 8m. Doesn't help us out because we don't get rid of the m's. We do 3n plus 5n, again we get 8n. It doesn't help us out. So, but if I see these same values, the same absolute value here, the same value, ignore the sign, you can realize that this would work out here in this example if we subtract the two equations. So you have 4m minus 4m, we now have 0m. So you can also subtract the equations. If we subtract the n's, we'll have negative 2n. If we subtract the constants, we'll have 6. So we'll find n is negative 3. And then we can plug it back into either equation. So 4m plus a negative 9 equals 11. Notice I multiplied 3 times negative 3 to get negative 9. So 4m is 20, and m is 5. Now we notice how we don't have x and y, and we have n and m. If you're writing as a point, you don't know which one is the independent variable, the x value. Put it in order, just put it in alphabetical order, and that's the common way of writing that if you want to write as a point. So this one here, same thing, but we want to try adding and subtracting. the issue is the x coefficients and the y coefficients are not the same or opposite. So we have to do something different here. And we can make them the same or make them the opposite by just using some of the equality tricks here, where we want to multiply both sides of the equation by the same value to make them become the same. So here, if I look at the y's, I have a negative 4y and an 8y. So if I multiply the top equation by a 2, both sides by 2, it gives us 10x minus 8y equals 6. If I rewrite the second equation, now I have opposite coefficients for y, which that will then allow me to add the values, add the equations to 12x. I now have 0y and then 4. So we find x is 1/3. If I divide by 12 and reduce, plug it back in, and I would plug it back in, maybe this bottom one here. So 2 times 1/3 plus 8y equals -2. So this is 2/3 plus 8y equals -2. But 8y is equal to, subtract the 2/3. So we're going to have a -2 and 2/3, which is the same thing as what? -8/3. So now I can divide by 8, which is the same thing as multiplying by 1/8. Multiply by reciprocal. So I have -1/3 as my y value. So there's a point, 1/3 comma -1/3. So I'll slow us down and repeat it if you need to go back and look at the mental math, but you should be able to do that fairly quickly. So here are the steps to go through to solve these if you're using a linear combination. It's just adding and subtracting the equations. You want to line up the like terms vertically, so the x's are above x's, y's above y's. Usually we like that in standard form. So if they're in standard form, it's a great method to use. You're going to multiply one or both equations by a number, so the coefficients of one variable are the same. And you could say same or opposites. If they're opposites, you will need to, you'll actually add the equations. If they're the same, you're going to subtract the equations. You'll then add or subtract the equations to eliminate a variable. Then you'll have one equation with one variable you can solve and then back substitute. So those are the steps to go through. Let me try another problem here. So right here, first thing I see is that they're not lined up. It looks like they are x, but I have an equal sign before the y. So I could rewrite that first equation as 3x plus 6y equals 12. And then the second equation, I would multiply by 3 to both sides. Make sure you do it to every term. So now I have these equations I can add to get rid of the x's. I get 15y and equals 30. So then here y is 2. I can back substitute that, put that in for a y value, it doesn't matter which one. Only I'll put it in here, so negative x plus 6 equals 6. So here x ends up being 0. So we have the point 0, 2. If you're not quite sure if that is a true solution, plug it into both equations. If I do that, and it does work out, yep. And just quickly think it over and check. So let's have you try this one on your own. Figure out which method works best. If you want to use substitution, I think that's best, or linear combination. Using linear combination, do you need a multiplier or not? Turn that in when you first walk in, and we'll see how that looks. And we have a little bit more to talk about for this section: parallel and or infinite solutions, no solutions, and one solution for systems of linear equations. So have a good night.